So this video will continue the periodic table trends theme, except for this video we will be talking about atomic radii, which is just a fancy word for saying how big is the atom. Now, the tricky part of measuring the size of an atom that I want to address here before we just roll into this is that if I were to measure the radius is half the distance, half the diameter, right? If this is the diameter, this would be the radius from here to here. Now, the problem with doing this for a single atom is that there's no clear border to the outer edge of an atom. It's a very fuzzy border, and if you think about it, the electrons, it's not like it's a solid wall out there saying, here's the outer wall of the atom. It's just empty space, really. The majority of the atom is empty space, and the electrons occupy that space in weird ways. So there's no good way to just say, okay, I'm going to take a ruler and measure from here to here. You can't do that. So scientists came up with a clever way to measure this. By what they did is they would bond the same atom together. So they'd take two hydrogen atoms, bond them together, and what you can clearly measure is the nucleus of this atom, the nucleus of this atom, and the distance between the nuclei. So you take 1/2 the distance between the nuclei, and then that gives you the radius of a single atom. So that's important because there's no clear defined border. The nucleus is very defined. You can't do this because the outer edge isn't defined. So you take two nuclei, bond them together, and then find the distance between the two nuclei because you assume that the atoms combine. When they combine, they stop when their electron clouds bump into each other. So they're kind of defining their own boundary for you. So just for the most part, you have to memorize this this definition: half the distance between nuclei of identical atoms in a molecule. But I want to at least explain why this is the definition. So the group trend. The atomic radius increases going down. And this should be pretty obvious. As you go down a column, you're adding more layers, right? Period 1, hydrogen has 1 energy level. Lithium will have 2 energy levels, 3, 4, 5, 6, 7. You're adding more layers, and to add more layers, you got to grow outward. They're going to get bigger. The atoms will get bigger going down. So why? Because you're adding more energy levels. I'll draw some pictures in a second. The period or row trends, the atomic radius increases right to left. Now this is counterintuitive in a lot of ways because you're like, okay, well, lithium has 3 electrons, beryllium has 4, boron has 5. As you're adding more electrons, you think it would get bigger going to the right, but it actually gets smaller. I'll explain that in the next slide. But the answer for now is electrons feel greater pull with more protons in the nucleus, is the reasoning. So we'll dive into that in a second. Okay, so the trend for going down, it increases going down. Why? Well, because lithium has 3 electrons, 1, 2, 3. Sodium has 11. The first 2 would go on this ring, the next 8 would go on this ring, and then the 11th one would go on this ring. Do you see why sodium's bigger? And then potassium, I'm assuming you can see that. First 2 electrons go on the first ring. Then you've got 8 electrons here. And then you've got another 8 electrons here. And then the last electron has to go on the 4th energy level. And you can see why potassium gets even bigger than sodium, because as you're adding layers, as you're adding energy levels, they get bigger. That's a pretty easy one for people to understand. It's intuitive, it makes sense. The next one, though, is not as intuitive. It increases left. Sorry, that should say right to left. Let's right to left. We're going to fix that right now. So right to left, it increases. Now, why does it do that? Let's look at lithium. Let's just look at the outer layer, the second layer. Let's not worry about the first layer right now. Okay, lithium has 3 protons in the middle. It's got 1 valence electron. Now, If I go on to beryllium, again, just worrying about the second layer here, beryllium has 4 protons in the middle, and it's got 2 electrons on its second layer. Now, what I want you to notice is that the second layer, we're not adding another layer here, we're just adding an electron to the layer that's already there. But what we are adding is an extra proton in the middle. More positives in the middle will pull those electrons in a little bit tighter. More positives has a greater attraction for those electrons. It will. That's lovely to be interrupted by the bell. It'll pull those electrons in just a little tighter. It's got a tighter hold on them. Then if I move on to boron, same thing here. We're not going to add another ring. We're just going to add another electron to the ring that's already there. But we are adding now, we have 5 protons. We added another proton. 5 positives is going to pull on those electrons a little bit tighter as well. So the atoms actually get smaller as I go across because there's more protons that are sucking that outer ring in a little bit tighter. Now it's not until I get all the way to neon, so they get smaller and smaller and smaller because these are all second energy level electrons being added, but the protons are pulling that second ring in a little bit tighter each time I add another proton. They get smaller and smaller until I go to sodium. Sodium, yeah, it has more protons, but now we have to add another ring, which makes sodium bigger again. And then as you move across this row, you got the third ring that's getting pulled in tighter and tighter and tighter as you add more protons, and that's why they get smaller going to the right. So let's practice here. Which one is bigger? Now, notice that the entire periodic table follows one trend for this. We don't have to divide it up into nonmetals and metals, whereas metals lose and nonmetals gain electrons. They all have a size and they all follow the same trend. Even noble gases have a size. We can start, they exist now, right? We've always kind of pretended like they don't exist in the reactivity trends, but they have their own size too. So what we're going to do is we're going to look sodium and aluminum. Look, sodium is here. We've got aluminum here. Sodium's further to the left, so sodium is larger. We've got nitrogen and neon. Now this is a noble gas, but that doesn't matter at this point because we're not talking about reactivity. We've got nitrogen and neon. Nitrogen is further to the left. So pause the video and try the rest on your own. Just take 1 minute, quick find them, and there we go. Hopefully you're back now. Gave you a little delay there to pause the video. Chlorine, bromine. Chlorine, bromine, they get bigger going down because bromine has an extra energy layer, or energy level. Titanium and calcium. Calcium's here. Titanium further to the left is calcium. Nitrogen and arsenic. We've got nitrogen and arsenic over here. Arsenic is going to have more energy levels. It's going to be bigger. Manganese and iron. Iron will have an extra proton which sucks in that outer layer a little bit, so manganese will be bigger. Calcium and germanium. Calcium is further to the left. Germanium's over here, by the way. Bromine and argon. Now, bromine is further to the left, and it's further down, so it's definitely bromine. Bromine has an extra layer. That actually brings up a good point before I forget. Let's say that I'm just going to erase everything here. Let's say I ask you about sodium and calcium. You'd be like, okay, sodium. Oh, thank you, Jordan. All sorts of interruptions in this video. That's okay though, Jordan. Thanks for saying thank you. Sodium is further to the left, but calcium is further down. Now what I want you to know is that the left to right difference is very small. The up and down difference is very big. So if you're down one, an extra layer will definitely make you bigger. So even though sodium's 1 to the left, it's not going to be bigger than calcium because calcium has a whole extra energy level. So I could give you kind of tricky ones like this on a test and be ready for them. We were at bromine, argon, I think last, right? Bromine. So know that the up and down is more important than the left to right for size. Nitrogen and sulfur. So we've got nitrogen and sulfur. So there we go. There's the exact example that I was telling you about. Sulfur is lower. That is more important than the fact that nitrogen's to the left. This difference is very little. This difference is very big. Potassium and magnesium. We've got potassium and magnesium. That's easy because potassium is to the left and it's down. And then krypton and chlorine. Krypton and chlorine, another tricky one. Krypton is lower. That's the important trend, or that's the important one to know there. And there you go. That should be it.